Hello and welcome to another review session for your final exam in Calculus 3208, presented by CDLI. Today we're going to be reviewing the topic of the chain rule, which is a very versatile and very important, useful rule for finding derivatives. So we're going to get started by looking at some of the key features of our little chat today. We're going to look at how do we formulate the chain rule, a couple of different ways to look at it. And we're going to look at how we use the chain rule in an algebraic context. And also, not just for chain rules, but we often end up using it in conjunction with the product and or quotient rules. So we'll look at how we do that as well. And then we'll talk about using the chain rule for some numerical questions. Okay, so let's get started. First of all, to do a formal proof of the chain rules can really be quite involved. And rather than getting into the details of that, since you're not required to reproduce such a proof for your final exam, I thought it better just to review the way the formulas look, and then we'll talk about using Leibniz notation down here, just a quick way that it's often been justified how we use the chain rule. So, first of all, we use the chain rule as a way to differentiate composite functions. And if you remember, a composite function like our h of x that we have here is just one function like g nested inside another like f. So what the chain rule tells us is to find the derivative of h of x, called h prime. Then what we do is we differentiate the outside layer, or the outermost function f, leaving the g of x that was nested inside alone. So we find the derivative of f sort of evaluated at g of x, and then after that we multiply by the derivative of g of x. So using the Leibniz notation, we think of y as being a function of u, where u itself is a function of some other variable, x. So it's kind of based on what we have up here. We're going to say that y equals f of u, and so u equals g of x, so then y is f of g of x, which is the same thing as our h of x up there. Okay, so by Leibniz notation, if I wanted to find dy over dx, or the derivative of my outermost function with respect to my innermost variable here, well, I'd have to differentiate y with respect to u first, and then multiply by the derivative of u with respect to x. So this is not really an algebraically valid way to prove this, but it sometimes gives folks a little justification to be able to say, oh, I can see now that the du business would go away and I just have a dy over dx. That's not truly an algebraic proof of this, but it does give you a little bit of a mental justification to help you soldier forward. The most important thing, however, is that we do know how to use this rule, so let's make sure we see in great detail how all that works. So the first example we're going to talk about here is using the chain rule to differentiate a couple of different power functions nested inside other power functions. So for the first case, we have y equals a square root function. And as always, if I want to differentiate a square root, I'm going to change it from being a square root into being just a power. So I'm going to call this 3x to the power 4 minus 5x squared plus 3. And instead of square rooting it, I'm just going to say that's the same thing as if I had it to the power of 1/2. So now when I want to take the derivative here, or differentiate, dy by dx is going to be equal to 1/2 of all the stuff that was inside without changing it. So this is my f prime of g part. So it's going to be 3x to the power 4 minus 5x squared plus 3. So I didn't change anything inside. I just differentiated the outermost function, which was that power of 1/2. So using the power rule, I multiplied by this in front and then reduced my exponent by 1. So that's part way through to the derivative. The next thing we have to do is, according to the chain rule, I differentiate the outside, leaving the inside alone, and then I differentiate the inside. So this gives me 4 times 3 is 12 times x cubed minus 2 5s are 10x. And if I wanted to write that in simplified form now, my numerator would consist of a 1 and this little binomial over here. So that's just going to be 12x cubed minus 10x. Divided by, in my denominator, I would have 2 times the square root function with 3x to the power of 4 minus 5x squared plus 3. Okay, and we could reduce this one step further, since both of these coefficients up here are divisible by 2. We could say that this is simply 6x squared, cubed, minus 5x all divided by square root of 3x to the power 4 minus 5x squared and then plus 3. So there's my derivative using the chain rule with simplifications. Okay? All right, let's try the next one. For the next one, if I want to differentiate, I'm going to find f prime of x here. And it's the same story. I've got a power rule on the outside and a polynomial inside. So differentiating the outside part, leaving the inside part as it is, I have this, and that's all to the power of 26. And then I'm going to multiply by the derivative of the stuff that was left inside. So 5 times 17 is 85 x to the power of 4, and the derivative, of course, of negative 11 would just be 0. So there that one is differentiated. Not much to do simplifying. I could multiply these two things together if I wanted, but we're not going to take a whole lot of time to look at simplifying that because there isn't much we could do anyway. Unless, of course, you wanted to expand 17x to the power of 5 minus 11 by itself 26 times. Good luck to you. Okay. Let's do another example. This time what we're going to do is we're going to differentiate a couple of functions here that require the chain rule, but not just the chain rule. We also have to look at the product rule because we have things that have nested functions here or composite functions, but we also have to deal with this whole idea of having a product rule or two things multiplied together. So kind of the reverse of each other are these two examples. In the first case, I've got this function right here, all raised to the power of 7, so that's a chain rule unto itself, but then it's multiplied by another function, all raised to the power of 7, which is another chain rule. But in the grander scheme of things here, I have those two different chain rules, but my whole thing is multiplied together, and where all that's multiplied together here, that's going to have to give us a product rule. So in the biggest picture, I have a product rule, and for each one of those product rules, when I go to differentiate, I have to use a chain rule. So this is going to be quite a lengthy response when I write all this stuff out. So we'll probably write it all out and then erase it all before we do the next one. So just to save ourselves some space here. Okay, so let's start off by saying we want to find dy over dx. And then I'm sorry about all the different colors, but I think it's going to be important for us to keep track of stuff. So the first thing I'm going to do is I'm going to find all of the derivatives of, or all the business with this first one. So I'm going to have to say that my derivative here will have to be, remember that the product rule says the derivative of the first one multiplied by the second one. So the derivative of the first one here is going to be 7 times x cubed minus 3x squared to the power of 6. But chain rule tells us that it's also multiplied by 3x squared minus 6x. So all that is just the derivative of the first part. And now I have to multiply that by the second part before I take its derivative. So the second part is this business over here. So I have the derivative of the first times this is the second, 3x to the power of 4 minus 7 raised to the power of 5. So I'm halfway through the product rule, which required a chain rule for the first part of it. Then I have to add, now the derivative of the second bit, which is the stuff that I've highlighted with this red bar over the top of it over here, the derivative of that now will be another chain rule, 5 times 3x to the power of 4 plus, minus 7. Okay, and then I'm going to have to raise that to the power of 4 because I reduced the exponent by 1, and then multiply by the derivative of the nested function, which is 12x cubed, and the derivative of negative 7, of course, is 0, so we don't need that. So that's just the derivative of the second bit, which now, by rights, has to be multiplied by the first bit that we had. So I'm going to multiply that all by x cubed minus 3x squared to the power of 7. So yikes, that's the whole thing. To differentiate this little product of two binomials here, I've got this huge and ugly looking derivative. But it's all about seeing the patterns in the structure and what we have here. So let's see if we can simplify this. Obvious simplifications. I'm not going to raise anything to the power of any binomials to the power of 6 or 4 or 7 or anything for this. So I'm just going to do the obvious simplification. So maybe the 7 can get multiplied by this binomial. And so I have 21x squared minus 42x. And then I'll just collect the other two and write them beside it. So x cubed minus 3x squared to the power of 6. And 3x to the power of 4 minus 7x to the power of 5. And then the second part of what we had there is I'm just going to multiply the monomial times this coefficient. So 5 times 12 is going to give us 60 x cubed, and we're multiplying that now by 3x to the power of 4 minus 7 to the power, all to the power of 4, sorry, and then x cubed minus 3x squared, all to the power of 7. So there's that lovely derivative. Okay. Now let's try the other one and see if we can compare what's different about the structure. So if you want to take a minute to write that down, you may wish to pause or something, because I'm going to delete it now so we can have some space to do part B here. So let's look at part B. In the first question, what we had to do was we had to differentiate what was really a product rule that had two chain rules sort of inside of it. In the second one here, what we have is kind of the opposite. It's really, in the grand scheme of things, I have a chain rule because of this big square root here, and inside that chain rule, I've got to differentiate a product. So I don't think this one's going to be quite as long, but still somewhat complicated. And before I do anything else, I'm going to make sure that I rewrite this so that I have, instead of a square root function, I'm going to rewrite this as a power function. So I use a big square bracket for stuff here, and inside I've got 5x minus 4 times 3x cubed minus 4x squared plus 2x minus 3, and all of that is raised to the power of 1/2. So now when I go to find my derivative for this, so notice I'm starting way back here to give myself some room. I'm going to differentiate the outermost layer first, which is the chain rule part. So I've got this big power function now. So it's 1/2 of all of that stuff without changing it first. So I'm just recopying everything inside those big square brackets now without changing any of it, because this is the first step in my chain rule. And I have all of this business. And I've got to change my exponent now by subtracting 1. So I've done the outermost business of the derivative. Now I have to differentiate what's left inside there. And this is where the product rule comes in. So I have to find the derivative of those two factors multiplied together in there. So using my product rule, I've got to multiply by the derivative of those things. So the derivative of the first one is just going to be 5, so that's nice, times the second, which is 3x cubed minus 4x squared plus 2x minus 3. And then I have to add the derivative of the second part, which we should be able to see here is 9x squared minus 8x plus 2. And I have to multiply by the original first part, which was the 5x minus 5, like so. And so I have all of that as the derivative of, sometimes it's a little bit disgusting, but some of my students say, well, sometimes you gotta, when you're using the chain rule, you take the derivative of the outside stuff and then multiply by the derivative of the guts, which is everything inside. Okay, so we could expand all of this stuff over here inside these brackets if we wanted to. But I'm thinking we're just going to leave that out, and we'll just write it as a quick simplification for now. I will multiply through by the 5 in the first one, and that'll probably be about it. So I'll have 15x cubed minus 20x squared plus 2x minus 3. And then I'm just going to add, I'm not going to write out this 6-term product over here. So it's just going to be 9x squared minus 8x plus 2, of course, multiplied by 5x minus 5. And notice that I didn't put any brackets around all of that to protect it, because what I'm going to do now is I'm going to change this business right over here to write it as a negative exponent becoming a denominator. So it's 2 times, and it's an exponent of 1/2, so we can call it a square root again. So this is a square root of 5x minus 5 times 3x cubed minus 4x squared plus 2x and minus 3. Okay? So that's a simpler version of all of that, but it's still, those are rather complicated things to deal with. So we're getting into some rather layered business here with product and chain rule together. Okay, something similar here, only now we're dealing with a quotient rule and a chain rule all sort of mixed up together. Okay, so in the first one, what I have is a quotient of 2 chains, if you want to think of it that way. And in the second one, I have a chain of 2 quotients. So let's get right down to it. So for the first one, dy by dx is going to be equal to the derivative of the top stuff. Will be 7 times this to the power of 6 multiplied by the derivative of the guts. So 3x squared minus 6x. And then I need to subtract the derivative of the top stuff multiplied by the bottom. I forgot the bottom business there, didn't I? Okay, so I better fix that up right away before we get any further here. So let's get rid of that. So we're going to multiply now by the bottom stuff, which was 3x to the power of 4 minus 7 to the power of 5. Then I subtract the derivative of the bottom, so that's going to be a chain rule unto itself again. So 5 times 3x minus 3x power 4, minus 7 to the power of 4, and multiplied by the derivative of the guts, which will be 12x cubed. And then for that, I've got to multiply by the business that was up top, so that's x cubed minus 3x squared, all to the power of 7 here. And of course, as always with the quotient rule, I divide everything by the bottom business, 3x to the power of 4 minus 7 squared, and since it's already power 5, that becomes power 10. Okay, so I'm not going to go through any simplification with that. I'll leave the algebraic details to you. Just want to show you how the structure works when I have to combine several of these rules together. Alrighty, so I'm just going to erase that now, and we'll tackle the second one that's there. So part B. Alright, so for part B here, what we have to do is we have to find the derivative, and this time I have the quotient rule nested inside the chain rule. So the first thing I want to do with this before I go and find f prime of x is rewrite this as a power function. So I'm going to say 3x cubed minus 4x squared plus 2x minus 3 all over 5x minus 4, and I want to see that as a power of 1/2 instead of as a square root. Okay, so now when I go to differentiate this business, I'm going to have 1/2 of everything that was inside, so 3x cubed minus 4x squared plus 2x minus 3 all over 5x minus 4 raised to the power of minus 1/2. And then I have to multiply by the derivative of the stuff that's inside there. So just let me grab this things I've written over here and move it up out of our way a little bit so we have some more space. Just going to move this stuff up here a little bit. Okay, so then I have to multiply what I have now by the derivative of what's inside there. So the derivative of my numerator is going to be 9x squared minus 8x plus 2 times the bottom stuff here, or the denominator, which will be 5x minus 4. And then I want to subtract the derivative of the denominator, which is 5, times the numerator. So 3x cubed minus 4x squared plus 2x minus 3. Okay, and then all of that gets divided by the denominator squared, which is 5x minus 4, all squared. And again, this time I'm going to leave the simplification out of it because I just want you to see the structure of the derivative. The simplification bit is just algebra. Okay? So let's jump on to one more example here, and it says the chain rule in a numerical context. So in this case, we have a table of values with a bunch of things about f, g, whatever. And in part A, it says we want to find h prime of 1 if h of x is the composition of f with g inside of it. So that means it's going to be f prime of g of 1 times g prime of 1. So the first thing I want to know from my table is what is g of 1. So I'm looking up here and I see that it's 2. And then I want to know what's g prime of 1, and I can see that that is 6. So to finish this, I need to find the f prime at 2, which I can see now will be a 5. So f prime of 2 is 5, and still multiplied by 6. So the answer for the first one here will be 30. All right, let's look at part B of this. So I've got k of x, in this case, is a composition of a function inside of itself. So g of x. So that means that k prime at 3, which we're after here, will be g prime at g of 3 multiplied by g prime at 3. So we need to first find g of 3. And so I look in the 3 row here, and g of 3 is going to be a 2. Sorry about that. And then G prime of 3 is what we need next for out there, and G prime of 3 is going to be a 9. And then the last evaluation here will be G prime of 2, and G prime of 2 we can see will be a 7. So this is 7 times 9, which should be about 63. Okay? So that's how we use the chain rule in a numerical context. All right, so here are the or turn questions, some more derivatives. And after you go through all of that business, you can check the solution. So if you want to pause it, go ahead. I'll jump to the solution now. So here's the solution, page 1. So the solution for the derivative of the first function, the one that's given in part A, with the full simplification if you want to practice that bit as well. That's all given for you there. And also, for the second one, there's the second your turn question, and it was a product rule with 2 chains inside, and all that's worked out in its gory detail. So you can check through all that stuff. Alrighty, so let's highlight some of the key ideas that we saw here. We talked about if we have a composite function, then we use this business where we differentiate the outside, leaving the inside alone, and then multiply by the derivative of what was inside. And we can apply the chain rule in as a composition of 2 or more other functions, and we can apply it in conjunction with the product and quotient rules, or we can even use it numerically from a table of values. And although we didn't look at an example similar to what we can do with product and quotient rule, you could also do that for something from a graph if you had to. All right, so that's everything you needed to know about the chain rule for a quick review. Hope your studying is going well, and good luck on your final exam.